I'll try to not spend too much time on the slides, but really dig into the code and the development aspects of this topic. All right, so first, let me start with a real-world scenario. Before I talk more about Stream Insight and about the cloud service that is offering Stream Insight in Windows Azure and Stream Insight itself, if necessary, I want to start with a very real, tangible user scenario that motivates a lot of the aspects and features that I'm going to talk about later. What you see here is a dashboard that gives insight into the user experience during the streaming of a keynote at a conference. In this particular case, it was the Mix conference last year. And what you see is a real-time dashboard that shows how the streaming is working for people in terms of buffering and session duration. So what this provides is an insight into the customer experience, basically, for that video streaming use case. What happened here is, if you look at the graphs, the average buffering at some point is going up and the session duration is going down. There's a direct correlation. The stream started to not work well anymore. The streaming clients, the Silverlight client in this case, people are watching through Silverlight clients, the clients started to buffer, and people got frustrated, eventually, dropped off the feeds, so the session duration basically dropped off as well. And this is a display that was updated every few seconds, every 30 seconds, I think. So it's really the real-time insight into what's happening into the content distribution. Why did this happen? The keynote happens on a first Tuesday in a month. I don't remember which month, March probably. And as you know, what happens on the first Tuesday every month? It's Patch Tuesday. So that was unfortunate, but there was some interaction with the content distribution network, and machines were patched automatically. Long story short, the video distribution and streaming didn't really work, at least for some users. And what happened then is somebody saw this on this dashboard, and instead of having to analyze the problems after the fact, after the streaming is over, when you can't really do anything anymore for these users, the problem was recognized right away, and then measures could be taken to improve that experience while it is going on, to make that it's only affecting a small group of people and only for a short period of time. So what I wanted to demonstrate here is the value of real-time insights into scenarios where I have telemetry data that I can process. The important aspect here is that the clients that provided the user experience, the Silverlight video players in the user's browsers, were instrumented with means to send telemetry events to a central service. Telemetry events about the user experience, like buffering, session duration, and interactions with the player, so that I can react on these events. I can aggregate them in real time, and then have a human consumer of that dashboard act upon issues. So just to motivate the whole use case and set of scenarios of event-driven processing of streaming telemetry data, and being able to act on that in as close to real time as possible. So that was one scenario. I want to touch upon a few other scenarios where an infrastructure that allows you to do such processing and aggregation of telemetry data from distributed sources comes into play as well. Typical example that we always bring up, infrastructure monitoring. So the goal here is to monitor large-scale cloud infrastructures, services in real time by grouping and aggregating performance counters, for instance, over temporal windows. Such analytics can be offered to the cloud customers as a service themselves. And part of this scenario is a spectrum of latency behaviors where a low latency monitoring experience can be offered, for instance, as a premium service, besides a default offering with higher latency. That could be one possible differentiation to provide such insights to the customers of a cloud infrastructure. The point is that aggregations over such different window periods can be run in parallel at all times, right? As a user, I shouldn't have to worry where do my insights into the telemetry come from. I should just be able to pick and choose what's the granularity of information and how often it's supposed to be updated. So that's kind of the gist of it. Here, the sources. The stream producing sources are machines, are a cluster, a fabric, a compute fabric that I want to monitor. For instance, to handle peak loads, load spikes, to ensure the SLA for the customer is fulfilled. Second one, and this is basically what I just talked about in the previous slide, the real-time monitoring of user experiences when consuming certain content, like in that example, streaming media. So that could be a video telemetry scenario or other kinds of consuming a user experience on a client and then on many distributed clients, all of which I need to collect telemetry from and then aggregate in a central place. Another very related and very typical scenario is web analytics, clickstream analytics from web browsers. Again, this is about processing, analyzing, and reacting to the customer experience of a website, say a web store where I want to do recommendation queries based on the existing user interactions in terms of clicks and search keywords, to be able to serve ads or adjust the navigational structure of the website. Again, what we have in common here is widely distributed sources, a high number of sources, potentially hundreds of thousands or millions of clients using their web browsers, and the necessity to collect and process these click streams in a central place so that I can aggregate over all of them in an event-driven fashion, in a near real-time fashion with low latency, and then being able to react on user behaviors on certain issues and situations, again, as close to real-time as possible. And lastly, we are also targeting vehicle telemetry scenarios, where here, naturally, the sources are cars, connected cars, which more and more cars are already being able to send diagnostic data or GPS location data to some central service where I can then try to recognize certain issues, certain patterns, do pattern matching over the diagnostic data events, or aggregate GPS data from a fleet or from a set of cars, and then reason about that. For instance, recognize certain traffic conditions and scenarios based on the complete set of GPS location data that I got within a certain time frame. Again, being able to react on these in real time, that's the target scenario. All right, so this is all about event processing. So far, I didn't really talk about where is the processing actually happening. What is the product that does it? What's the infrastructure? What's the deployment? What's the compute fabric here? I will mention Stream Insights as a product, and I don't know how many of you know it. In a few slides, I want to introduce Stream Insight itself as the Microsoft event processing platform that is released as an on-premise product. And what I wanted to do here now is to motivate why would we use the cloud for these scenarios, for these types of processing of streaming event data. And we see two, I would say, categories of scenarios that justify this effort, justify a service in the cloud. First of all, the event data might already be in the cloud, like the clickstream analysis, right? I have web browsers going against web servers. The web servers are in the cloud. That might be the Microsoft Azure cloud or something else, but the machine-born data, the generated data, is already not really an on-premise generated data. So I'm already in the cloud with the data. In another set of scenarios, the event data might not be generated in the cloud, but it is already globally distributed. For instance, the connected car scenario, where I have cars that produce data that are geographically distributed, or weather sensors, or aggregating over plant floor data of multiple plants, multiple sites within a geographic area. So the data I want to aggregate across these geographically distributed sources is already has to travel over the network, whether it's traveling to a central cloud service to be processed or to an on-premise deployment. Doesn't really make a difference for the data sources, right? So what both of these have in common is the data is not local, right? And that justifies our paradigm here. What we want to convey is bring the processing to the data, not the data to the processing. And beyond that, of course, there are the typical cloud benefits. Typical benefits of running a service, not having to maintain a data center, reduce total cost of ownership, being able to scale out more or less elastically, right? Provision more compute resources for a certain use case in a comparably short period of time, maybe even elastically adapting to current throughput of data, right, without a human interaction. And then lastly, being able to use a service instead of having to maintain an infrastructure. The service that I will now talk about in more detail that does the event processing includes things like, oh, I think I just lost the slide deck. Interesting. I don't know whether you saw it. All right. Includes things like a monitoring service that automatically restarts the service or the queries if something goes wrong. It includes a management interface so that I have a single system image, even though my event processing platform runs on multiple cores or even multiple VMs in the cloud. So having a service instead of an infrastructure is one of our design goals here. All right. So I mentioned the name Stream Insight already, and again, I'm assuming that some of you at least know the product Stream Insight. The effort to provide Stream Insight in addition to the box product as a service in Azure currently runs under the name Windows Azure Stream Insight. It's not signed off with marketing yet, and I should also make clear this has not been released, right? So everything I'm going to talk about is a service that runs as a CTP. So it's out there in the form of a preview, but it hasn't been released and the name hasn't been finalized. The code name is Project Austin. You might have seen or heard about Project Austin. That's the code name for the Windows Azure Stream Insight service running in the Microsoft Cloud, right? So let's start with setting up that whole use case. What is the architecture? What's the basic interactions here? Well, we have the Azure Cloud. We have an IT pro, say, that realizes the need for event processing, for a Stream Insight deployment, with regards to the scenarios that I mentioned earlier. Eventually, what this person would do to get to a Stream Insight deployment is to go to the Windows Azure portal. Right now, this is not Stream Insight is not on the Azure portal yet. We run a private CTP that only has programmatic APIs. Eventually, this is a service that is supposed to be part of the ecosystem of Azure, right? You go to the Azure portal, you can provision compute and websites and storage and SQL Azure and Service Bus, and eventually also Stream Insight. So that will be the model of the interaction. The Azure portal would then go against the APIs and create a Stream Insight instance in the cloud. The user could also go directly against the APIs, and this is what we are currently offering. Similar to other Azure services, there is always a UI aspect and there is an API aspect. So I can create a hosted service with the Azure portal through the user interface, I can also use the REST APIs for that. So we are following the same principle. We are making the management of Stream Insight in Azure available through the portal as well as through a REST API. And I will demonstrate the REST API in a second. As soon as I have this Stream Insight instance up and running, I can start flowing events. Right, I can develop my application against it, and I can define my data sources and my data sinks, and corresponding to the examples, the scenario examples I gave before. Those data sources could be phones, tablets, web browsers, cars, connected cars, machines, sensors, everything that produces machine-borne data. Configured in a way so that it is streaming into that cloud deployment of Stream Insight, and I will talk about the exact interfaces here for the streams. Then I have my own Stream Insight application running in that instance that does the event processing, that does correlation of events, aggregation over time windows, specified as declarative link queries. And from there, the results that are produced eventually go into the event consumers. And that's again something that I, as a Stream Insight customer, can configure. Where do my results go? Where do my aggregations go? That could be a storage, for instance, SQL Azure, Azure Storage, Azure Blobs, persist that, and then have a dashboard pick it up from there, and that's going to be part of my demo. I could stream that into Service Bus and then use that interface to go over the network to another consumer of these events. Or I can still define my custom event sync, just like I can for the on-premise Stream Insight products and platform, still write my own custom event sources and sinks. I can use that same interface, the same APIs, and the same way of development also with the cloud service. So that was kind of the big picture. I mentioned this, the APIs, the REST API a few times. So at this point, just so that there is no slide overload, I would like to go to, and I will share that now, a sample solution in Visual Studio. I'm sharing my desktop. And what you see here is a Visual Studio solution that we provide with our CTP. So the CTP of Windows Azure Stream Insight, also known as Austin, comes with an SDK that you install on the client, just like you would install a Windows Azure SDK or Service Bus SDK. You also install a Stream Insight SDK that lets you develop Stream Insight applications on your client that eventually will run in the cloud. And the sample demonstrates these application development aspects as well as the bootstrapping to actually get the service up and running. Since we are not on the Azure portal just yet, this is how you would currently, I say currently, with the current CTP, get your Stream Insight Azure instance up and running. And this is the currently active project here, services provisioning. It is really, there's no Stream Insight relationship with the SDK here. So you see the references don't include anything Stream Insight specific because all this project is doing is using a REST API. So it's doing plain old HTTP requests to the specific URIs of the Stream Insight management service, requesting an instance of Stream Insight, right? And the only thing a user here, a sample user like me now, would need to specify is in the app config a few parameters like how big is that instance supposed to be. Stream Insight in Azure scales out over multiple cores and VMs. And the current way of specifying the size of the deployment is kind of similar to how I would specify that for hosted services, where I have a way to define the size of the machines and then the number of the machines. And here I do something very similar. I can specify the size of the compute stage and then the size and the number of nodes for the ingress stage. And later I will talk more about what those two stages mean, but they all contribute to the compute power of Stream Insight. So I'm defining the size of my deployment. I'm defining a port for the data ingress, and that will be relevant for my data sources that stream their event data into that instance. They will need to address that port and the corresponding URI. And then I can also define, do I want to use HTTPS or just plain HTTP? in case I need to encrypt and validate the service address and make the data ingress a little more secure. And again, this is the current status. We're going to have more security features as we go closer to our release, to our GA. So just to demonstrate that, I will run this project. This is what you would see if you sign up for our CTP and if you download the sample and run it the first time. First, you have to create a few things in Windows Azure. Since we are not directly integrated into the portal, you would have to create an empty hosted service that we then use to provision into, and this is basically the process. The provisioning project creates a few certificates that you will either use to connect to the service, and what happens right now is it goes through a Windows Azure deployment. And as you know, this takes 8 to 10 minutes, sometimes more. This is what we'd have to go through in order to bring up these roles that eventually represents the Stream Inside service. So I'm not going to wait for that. Just wanted to kick it off and show how that works. That would be how you would currently work with the sample and set up your instance. Okay. Going back to the presentation. So I mentioned Stream Inside and the concept of streaming data a few times. I don't know, this is not an audience where we can do a show of hands. I think we have enough time for me to quickly go through the high-level concepts of streaming data and Stream Insights that are kind of necessary to understand in order to, talk more about the cloud specifics of Stream Insight and of the service. So the usual example, the usual setup we use to explain streaming data as we understand it, as we in the Stream Insight team in SQL Server understand it, is this parking lot example. Some of you, I'm sure, have seen it. If you have seen any Stream Insight presentation, you have seen that example. So let's try to motivate the paradigm, the notion of streaming data with an analogy of a parking lot. Imagine the question, how many red cars are in a parking lot? Well, if we assume we are a relational database, the analogy here would be to walk out to the parking lot, walk through all the rows, and then count vehicles that are fulfilling that predicate, being red and being a car, right? So there's a very clear corresponding SQL query, easy to understand, and that's how I would fulfill an ad hoc query against persisted data, right? Let's look at a different question, though. How many red cars have passed a certain point on a highway within a certain time window, time period? The photo here looks like a Seattle highway, which is more like a parking lot, but that's not the point. So assume that the cars are actually moving, right? Moving fast on a highway. So if we try to keep that analogy with a relational database, you see it's not really working anymore because for a database, data needs to be persistent and static. So I would have to take all the cars, pull them over, park them in a lot, and then keep them there for a certain period of time and count them there as I did before, and then release them back to the highway. Obviously, this is not really a good solution here. It's not really feeding that scenario. So we realized different kinds of questions require different ways of answering them. Specifically in that case, answering the second question with a stream processing engine drastically simplifies that use case by just standing by the freeway and counting the red cars as they pass by without even interfering with the flow of cars. And at some point, writing down an answer and deliver the answer. So that's kind of the streaming data paradigm in a nutshell for us, asking questions about data that is in flight without having to persist the data. So that's one of the core design principles of the Stream Insight product, on-premise as well as in the cloud. There's no difference here. Data is not stored, and processes are not transactional. Queries are not transactional. Data is kept in memory as long as necessary, defined by my queries, like windows in time. So the engine knows how long to keep the data in memory. And then the data is discarded. The result is produced, the result is passed on to the consumer, and then the data is discarded. That's not needed anymore. So there is no persistence, which enables the engine to be really fast. And not only fast, but also event-driven. And that's one of the, I usually find that even more important than performance is being able to be event-driven, to react on input as it is happening, and not based on some reporting frequency or workarounds, I would say, quote-unquote workarounds like triggers in a database. It is really, the engine is really processing the data and incrementally updating the results as soon as new input data comes in. So my output is always as current as it can be, with a latency of what we are targeting within the millisecond area. So that's kind of the paradigm, which is really very different from classical databases because the problems are very different. Few scenarios for Stream Insight, and again, this goes back to the on-premise product of Stream Insight, and some of these still apply to the cloud. I don't want to go through all of them. Maybe just pick a few examples. Manufacturing, specifically in batch processing use cases, there is this concept of the golden batch. A golden batch is a product batch with very high quality. Once such a golden batch is determined, the goal is naturally to recreate production parameters as they occurred during the golden batch, as closely as possible. Provided that these parameters can be measured and also adjusted in real time, a complex event processing system like Stream Insight can be used to create that real-time feedback loop with low latency analytics over the incoming sensor data. As you can imagine, there it's not really desirable to store all the measurements, all the sensor readings first in a database and then query the database, because with the increasing amounts of data, with increasing throughput, the I/O costs just become a big challenge. So I want to process the data as it is in flight. Another scenario is the streaming analytics over user clicks on a web property, and I mentioned that briefly before. I want to talk about it again because this is another real-world scenario that actually has been implemented in the Microsoft online property platform, Ad Center, providing ad placement services on the Microsoft sites and online properties like MSN and Hotmail. So that was a very early engagement within Microsoft using Stream Insight, where interactions of users with a respective web page, like clicks or search keywords, are streamed into a Stream Insight deployment in real time without the indirection of storage. Within the Stream Insight framework, the click streams then run through different analytics or standing queries, as we call them. For instance, a market segmentation query determines a user to be a promising target for ads for a certain market segment. And then these ads are served within a few seconds while the user is browsing the site. Before Stream Insight was used for this use case, the process had a turnaround time of several hours. So it only made sense for ads about big consumer items where the decision process takes longer. Makes sense for people intending to buy a car, but waiting a few hours with an ad for, say, a meal delivery, a pizza delivery is, of course, not practicable. So reducing that from hours to seconds opened up a whole new set of use cases. How does Stream Insight look like? Well, again, we usually start with event sources producing event data, proprietary event data. Could come from web servers, devices, sensors, could also be replayed from event stores and databases, persisted time series data that needs to be replayed to be analyzed again, or things like stock tickers and news feeds. All of these data sources stream their data into a Stream Insight server, assuming a Stream Insight application and use case. And they do that via what we call simply event sources. Those are pieces of software that the user has defined, either through .NET interfaces like iEnumerables or iObservables that can be turned into a Stream Insight event source, or through our traditional adapter model, which is an API, part of the Stream Insight SDK, to wrap my data sources into stream sources for Stream Insight. So from there on, the streams become kind of a canonical stream format, and they can then go into the queries, the standing queries, the computations that the user wants to run against the streams. I can compose queries one on top of the other. I can build more complex use cases based on simple subqueries. And eventually the results go into the counterparts of the sources, which are the event sinks. Again, those are user-provided assemblies, can be based on .NET sequences, can, for instance, just be an iObserver, in that case, the counterpart to the iObservable. And from there on, I can just dequeue the events and then consume them. And consuming events, that, again, is up to the use case and up to the developer. Could be to store them in a database after I have sufficiently reduced the data rate using an aggregation query. I can now store them, display them on a dashboard, like in the example with the streaming video, telemetry analytics, or stream them over the network to some other consumer. All of this is based on the Stream Insight library, basically the SDK, the platform that you get if you install Stream Insight. And I'm now referring to the on-premise product, where the Stream Insight server runs on my machine in my process. And all of this is it's a developer experience, it's a developer platform. So what's important to point out here is Stream Insight as a product is not an end-to-end solution with a fully baked UI. It's a developer platform that needs to be integrated into a bigger picture using other pieces like event sources, event sinks, and the UI. So it is heavily based on .NET developer experiences like Visual Studio. We also provide a link pad plugin so that you can use the lightweight link pad interface to quickly test, learn, try out, prototype Stream Insight queries against simulated data sources and things. How does a query look like? I've talked about queries a lot. Now, how would I write such a query? What you see here is a very simple example of an aggregation over a time window. In this case, I'm creating a window that is 10 seconds long, and within this window, every 10 seconds, I'm computing the average of a certain field in my incoming event stream. So naturally, what this query would produce, as soon as it is up and running and receiving data, every 10 seconds, it will produce an output of one value representing the average of all the values within the incoming window, which could have been 10 or 10,000. It's producing one output for each window. And so this is LINQ. For those of you who know .NET or even just SQL, that's a very familiar way of specifying analytics and computations, extended by the Stream Insight specific interfaces like tumbling window. That's something that the Stream Insight SDK adds to the LINQ developer experience. So let's go back to the cloud now. I hope that I could sufficiently introduce Stream Insight as a concept and as a product. But what I really want to talk about and motivate here is to take that platform and make it available as a service in the cloud, as opposed to having to install it on a machine, having to maintain it there, having to scale out manually across machines. All of that is supposed to be provided by the Azure service, Stream Insight. So going back to the interactions here, the IT Pro persona using the Azure portal to interact with the existing Stream Insight instance. What are the other interactions here? So the IT Pro has provisions. Now, how do we go from there? Well, we're assuming there is somebody like a data architect that knows about the event sources and the data formats and properties provided by the event sources. So the data architect is defining where the data is coming from and where other data, maybe reference data, is coming from that's not real-time data that needs to be correlated with the real-time data, and setting up that end-to-end pipeline in terms of defining the schemas, defining how the data is supposed to be correlated. There is a different role. There might be the same person, but a different perspective on such a scenario, on such a use case, is the data scientist's view, is what can we learn from the data? What kind of insights do I want to get out of the data? What kind of algorithms and computations and pattern matchings I want to apply to the incoming data. So the data scientist might be used to analytical tools, statistical tools like the R framework to specify these models, specify what is actually supposed to run over the data. And then eventually there is the person that is supposed to put it all together, the solutions architect, or in our case, the developer or the architect with developer expertise, to be able to take that input from the data architect about the event schemas, take the input from the data scientist about the actual computations, the semantics of my analytics, put it together in the form of queries that are understood by Stream Insights, and build that end-to-end solution. Using Visual Studio, using developer tools to create that application and define the processes and expressions, and eventually manage them as a running application so that data flow can happen, the processing is producing results that go into the event consumers. How does that look like in practice? Again, I would like to switch back to Visual Studio and show you, well, there you go, my service has been provisioned. So I now actually have a Stream Insights instance in the cloud that I could use. I won't do that right now, but I want to show you another project within our sample CTP solution, the sample application. So the sample application is what I, as a Stream Insights developer, would now actually write against my cloud instance. And what's important here to understand is there is an aspect that is developed and even run on my client here on premise, and there is part of the application that gets shipped to the cloud and eventually runs there. And sometimes it's not quite clear to see the boundary between those two, because what we are providing with the Stream Insights SDK is a very high-level declarative developer experience. It's based a lot on LINQ and reactive expressions. So this enables the user to develop on a very high level, on a very semantic level, without having to be concerned about things like procedural processes, scheduling, memory management. All of the heavy lifting is done by the engine and by the framework. I just have to specify on a very high level how the queries are supposed to produce results. So this is a fairly simple application here. The first step that you would see here, the very crucial step in the beginning, is to first connect to my Stream Insights Azure instance, right? The instance that I just have created with the provisioning 20 minutes ago. So I would call that API, that server object is part of the Stream Insights API, part of the SDK that I get as soon as I install that. And I would create that connection, and with that I have this server, I have this handle. I have a handle to the cloud instance. And every subsequent process is happening against that cloud instance. For instance, creating an application. This is another notion, another concept within Stream Insights is an application within my server. It's kind of like a namespace in C#. I can create different applications that can host different queries. So you see it's happening against the server. So if I execute this project, this code, and this line here on my client, it will go against the web service on my cloud instance and will create the application there. So I still need that client experience. I still need an application that runs on the client, interacts with the cloud instance, and instantiates entities and queries in that cloud instance. So there are some more details here that I don't want to get into right now, but what I do want to show is how I set up that whole end-to-end pipeline from the beginning to the end. First is the beginning is where do the events enter my cloud instance, right? What do my event sources eventually have to do to send data? Well, we are using an HTTP endpoint that's built into the service that represents the data ingress for clients. And this comes with the provisioning. It has the name of the service. So I used a certain DNS prefix, just like with Azure hosted services. And then, as you remember, I was able to specify a port number as well. So that's going to be my data ingress endpoint. So my cell phones, my connected cars needs to send data to this endpoint. And what I specify here in this whole expression is how this endpoint is supposed to process the incoming HTTP packets, right? And it's a reactive expression. It's a declarative expression on an observable of HTTP packets, where I can take each of these packets that might be HTTP GET request with a query string, so I can actually go through the query string of the URL, or it could be a POST request with a body. Could be XML body, could be a JSON body, or some custom serialization. I have access to the body here as well, and I can convert that. I can call my user functions here, as I do, for instance, with that constructor. And I can convert that to a .NET type, in this case, an HTTP message with certain fields. So from here on, what I created is a conversion from an HTTP stream into a stream inside stream. So I have this HTTP source, and now I can use that to write queries against it. Okay. So what you see here is I take this HTTP source and I define what are the temporal properties. Where do the timestamps come from? This is something crucial in Stream Insight. Since it's all about time, it's about correlating streams in time, it's about aggregating within time windows. I need to tell the engine what is the time field, where does the time property come from in my event stream. So that's what happens with this call. And from here on, I can write temporal queries like take that stream, group by a certain property of the stream, creating partitions, subpartitions, and then do some aggregation within a window for each of these partitions, like a window of 5 seconds, and then building the average of a value, right? So from here on, I can define my computations in the same declarative language as I would do on-premise. Nothing here except the HTTP endpoint is specific to the cloud. The whole query language is the same as on-premise. And then eventually, I want to combine the queries with my data sinks, and I have defined them in the same piece of code, a little above, but I don't want to delve too much into the code right now. I have defined my sinks as stream consumers, and then I just take my queries, use the SDK calls like bind or with to create that end-to-end pipeline that enables me to eventually run the process. So at the very end, I need to run. So I actually got that here too. I define my pipelines with the sources, with the queries, with the sinks, and then run them. And again, it's important to note here that this line will be executed in my client application here on my machine on-premise. But it will not run the query on-premise. It will actually talk to the cloud service. It knows where it is because I created that connection earlier. It will talk to the cloud service. It will serialize the queries as a Stream Insights operator tree, and it will then tell the cloud service that's the query, that's the data source, that's the data sink, and now run this query in the cloud. Right? So everything I'm doing here in this piece of code is basically just defining things and communicating to my Azure instance to run it there. Nothing is really run on premise here. As soon as I pass this line, what you see here is that the application actually ends right here, right? So that the main routine of my console application ends here, and it will just stop and be done while the cloud instance has started the queries and runs them as long as I need to. Okay, so it's kind of a learning curve in the beginning to realize what is client, what is server, and what are the types of interactions. But it's very high level, very declarative, and it makes the code very easy to understand and easy to maintain. Good. Let me switch back to the slide deck. And I want to check whether there are any questions in the Q&A. Not so far. Okay, so let me just continue. So I talked about the architecture of Stream Insight before with the core engine that does the event processing, that executes the queries that I have defined, like the windows and the aggregations, and that does all the low-level stuff, like managing the memory, scheduling the operators, everything that I don't want to do because I want to use a platform, right? I don't want to code this from scratch. That's the value of Stream Insight. How does that relate to the cloud? How does Stream Insight run in the cloud? Well, as I said before, we have created a service here that goes beyond the core engine that I get with the on-premise product. Providing a service means to manage it, to monitor it, to provide an easy way to get data in and out. And this is where I want to start here again, is with the data sources, tablets, phones, web browsers, cars, oil platforms. First, we're collecting the data from them. And as I've shown in the sample, this happens through a built-in, automatically provisioned HTTP endpoint. So any device that can speak HTTP can submit data to Azure Stream Insight. It's not Stream Insight specific. It's not even platform or OS specific. The HTTP standard is old and well understood, and as soon as a device can send that, it can stream into Stream Insight. So there's the collection phase. From here, we go into what we call the ingress stage. And the ingress stage that's already part of the Stream Insight service is supposed to initially process that incoming stream of HTTP packets, which might mean to decode them, deserialize my HTTP bodies into the actual event data, the payload data, the values from my GPS devices in the car, or the telemetry values from the user experience events from the Silverlight video player, and also transform these events. For instance, enrich them with geolocation data. Typical thing that could happen on the ingress stage is to take the IP address, the client IP address, and translate that into an actual geolocation, and put that into the events as an enriched event format. And as I mentioned before, ingress runs on one or more cores. So here we're using the Azure Compute Fabric infrastructure. So when I provision my instance in the beginning, I can specify I will need 12 cores for that because I have to do a lot of lookups against my geolocation database, or I need to do other things. I need to do authentication and deserialization. That's compute intensive. So I want to run these things in parallel, not just on one core or one VM, but on a set of them. So that's already a scale-out aspect that does not exist with the on-premise product. One feature to point out here is the ability to not only process the data as it comes in, but also on the side record it. We call it a spool. Spool the incoming raw data to Azure storage. In our case, it's blob storage because it's the fastest, so that I can later do some offline processing of the data. I can take the data and do data mining, try to find new computations, new queries based on historic data, and use that for offline processing, maybe even with MapReduce infrastructures like Hadoop, and trying to integrate those frameworks from the real time to the historical processing. So that's another feature that provides a value add. Actually already right there, even if I don't go any further, if I just use the collection and the spooling, I already have a nice way to collect data in the cloud. So far, that's what it is. I have an endpoint that's built in. My clients can start streaming into that endpoint, and I turn on the spooling, and I will end up with blobs of incoming data, and then I can do something else with it. So that's one of the value props here. But the main aspect, of course, is then the processing, the temporal processing of the streaming data in the Stream Insight engine. And this is what we would call the analytics stage. After the ingress stage, we go into the analytics stage, again, scaling out over multiple cores, and now doing all the sophisticated event processing. filtering, analyzing, aggregating data over windows, correlating of multiple streams, detect certain patterns in my stream, like my event A, say, alarm on has been followed by alarm off within 5 minutes, so I know it's only a transient alarm, so I can ignore it. All these sophisticated things that are happening over time, they are processed and executed in the core Stream Insight engine. That's what we would call the analytics stage. And again, what is processed there, what executed there, is what I have defined in terms of link queries, what you have seen in Visual Studio before. That is what is eventually executed there. And from there on, we create results which go into the event consumers. And in the cloud, typical candidates here, SQL databases, Azure storage, custom event sinks like Service Bus, like custom WCF services. We want to provide some of these interfaces out of the box. In the current CTP, we're not quite there yet. Part of the sample is an Azure table sync, but that's really just a sample demonstrating the feasibility. It's not optimized or anything. Eventually, when we go into a general release next year, we want to provide some of these important interfaces out of the box. But there is still the possibility to define, write, and deploy my custom event sync that is then running in the cloud. As well as, by the way, a custom event source. I can still circumvent the built-in ingress stage with the HTTP endpoint by providing my own custom source and use that to stream data into Stream Insight. These stages that are part of the service also have a management and monitoring aspect. So when, for instance, Azure decides to migrate machines, right? It can happen in Azure anytime. Then obviously the service needs to make sure that the queries keep running, that the service of the migrated machines is started again and picking up from where it left off, and the queries are running again. So there's a whole monitoring and management layer on top of that that ensures that I have a nice service experience, not just the infrastructure, and I have to take care of that. That comes with the service, and service management have these endpoints I can connect to control my instance and get diagnostics, same as on-premise, where we have the diagnostic interface to get statistics of my event processing, like throughputs and latencies. Same in the cloud. You can actually use the same interface, the same tool. We have this, what we call the debugger, the UI that you can connect to a Stream Insight server to get that statistical insight. You can use the same tool to connect to an Azure instance of Stream Insight. Just looks the same way. Okay, I want to run through a few of the design goals and features and capabilities. And that won't take long because I mentioned most of them in passing already. So for connectivity, what we want to ensure here is that beyond the bare Stream Insight server, we are able to reach out to event sources and sinks, which is facilitated by the RESTful HTTP endpoint that clients can use to get data into, and then having the ability to write expressions over that incoming stream to do enrichment, geotagging, transformations. From there, we provide the analytical capabilities, being able to write the time-based queries, the windows and correlations in time, but also plain sequential queries, reactive queries. Stream Insight, since its latest version 2.1, in the cloud as well as on-premise, is becoming a host for both kinds of event computations and queries, whether it's time-based or whether it's plain sequential without time as a special property. So Stream Insight is basically a host for reactive and temporal queries. And then scale. One of the important aspects here is to be able to run that transparently across Azure cores without having to scale out manually, which is what people need to do on-premise. Since this is not a built-in feature, it's not very complicated, and we see many use cases doing that, scaling out over multiple machines, but I have to do it myself. In the cloud, we are providing that as transparently as possible. Security I mentioned briefly in the context of the endpoint with HTTP and HTTPS. In addition to that, we also want to provide client authentication, not just service authentication with SSL, also client authentication. We will eventually, we are planning to use ACS for that. And one other security aspect is that, and I will talk about that also later, is the fact that we don't share Azure instances. It is, in fact, a single tenancy service where the cores and the VMs that I request for my streaming side instance are dedicated to me and to my queries, and nothing else runs there, which makes security and privacy much easier. I briefly talked about monitoring, being able to, for the service, being able to automatically restart computations, queries, and the whole service, and also being able to send out notifications. So that's one of the service aspects we're providing, as well as tooling support, being able to log and trace in my user code. You've seen that there's a lot of, or there can be a lot of user code running. I can deploy DLLs to the Azure instance that are then called from within my queries. And that means that potentially procedural user code is running there, and I want to be able to trace from there, because naturally debugging in the cloud is difficult, right? I don't have direct access to the machine. I don't have good insights into what's happening at any point in time, so I need tooling for that. A feature that we are planning that is not yet part of the CTP or the service, but eventually will be, is to run instances redundantly. And this is just corresponding to Windows Azure hosted services, where you can say, I want to run that role on 2 or more instances, just to get some SLA for Azure. Well, of course, we need to do the same thing to eventually make outages really transparent. And that's one of the design goals that we're currently working on. I mentioned the spooling, the ability to record the raw incoming event stream to storage, and then use that for later offline processing, backtesting, auditing. And the Azure integration is another very central design goal for us. Consists of showing up in the Azure Management Portal, being part of that Azure ecosystem of services, being able to easily combine and couple the experience of Azure Stream Insights with, for instance, SQL Azure by seamlessly persisting the streaming results into a database or into Azure storage, and of course be integrated into the billing experience, showing up on the bill and make sure that I have a consistent view of everything I do in Azure, including the Stream Insight service. All right, I actually want to run a demo. I only showed code so far. Just before I started the presentation, I noticed it was not running. So let me see whether I'm lucky now and my demo is running. What the demo is doing is it uses tags. I just brought up, and I hope you can see my desktop. I brought up a Microsoft tag, which if you scan that with your cell phone, creates a call to a URL. And I'm using that as my data source with my cell phone, and you, if you want to use it, representing data sources that send data to that URL, which then gets processed. It's the HTTP endpoint of an Austin service, in fact, and so the events are processed within that service, and the results are streamed to 2 consumers. One consumer is a map that's supposed to show where those tags have been scanned, provided you enables the location feature of your, if that's a Windows phone, of the search application. And the other consumer is simply counting of user agents. Depending on what agents you use, whether it's a Windows phone or something else that uses not Internet Explorer. And I can reason over that, and I can aggregate that in Stream Insight and then display that on a web page. So Actually, let me try it first with my own cell phone, seeing whether it actually works now. Calling out to the URL, which should cause the HTTP endpoints to be called. Yeah, I think it did. You see that the count updated, and the count is within the last 10 minutes. So the other results didn't update because there was nothing updating the account. But the IE mobile just shows my own scan. And if you want, I can leave that page open for a while and talk about it while you are hopefully able to scan that tag with your cell phones on your screen. Again, if you have the location enabled, which is not enabled by default, you should actually show up on the map, depending on where you are. And I'm assuming somewhere in the US for most of you. If not, we can zoom out. And you should also see the user agent counts being updated. So I want to leave that open for a while. And while you're trying to do that, oh, okay, somebody else can apparently. So IE mobile went up to 2. So there's some success here. That might have been, oh, and I even get locations that are neither in Seattle nor in the Atlantic, which is the default for, latitude and longitude 0. So you see something's happening here. What is actually pretty remarkable is that it's pretty fast. It involves a lot of moving parts. There was Safari. There's an iPhone user out there apparently. There's a lot of moving parts. And scanning the tag, something that takes 1 to 2 seconds for the whole round trip. And this is actually pretty remarkable, not just regarding Stream Insight, but all the other parts that are involved here in terms of cloud services. There's service bus involved, there is Azure storage involved, and I'm going to walk through that. Just shows as a nice toy example that those tags can be used for something useful or for something that gives you actually pretty interesting insights into user experience, which is the location, which is the user clients, and it could be much more than that. All right, so let me go back to the presentation here. Actually, before we do that, I have a tag simulator just to show you that this actually scales pretty well. This tag simulator is just sending random HTTP packets, or I shouldn't say random, but from random user agents and random locations, simulating hundreds of cell phone users scanning this tag across the country. So if I start that, now that's what you would see. So you see things are really updating fast now. Also, the web page is pulling data from Azure storage. So the web page has a natural refresh frequency of 3 seconds. But the map that you see is, so that's the actual frequency of the query, producing results, pushing it over service bus to the map. And I provisioned that sample, that toy demo on, I think, one small ingress and one medium analytics. So it's really not using a lot of compute resources, and it could go way beyond that data rates. We are looking at data rates of several 10,000 per second. What I'm doing here is a handful per second at most. So it's really just showing the principle, not really giving a performance indication. All right, I will just let that run. And I will go back to the presentation to walk you through that use case, that end-to-end scenario of processing those tag events. Where are we? Where's my live meeting? All right. So we are starting with phone scanning the tag, which creates an HTTP URI, a request to a URL. That's what it effectively does. If the location is enabled in the Windows Phone specifically, that's I think a Windows Phone feature, then as part of the URI, as a get string, you know, with the question mark and then the key value pairs in the URI, also the location, latitude, longitude are included. What is also included with any HTTP request, naturally, by definition, is the user agent string, which is a fairly convoluted string, actually. So we get all that raw information to that URI. That's how I defined my tag. You know, I registered this tag and defined it as going to this URI. So that's what happens first if you press the, you know, the I and the scan on your phone. As soon as it goes into that URI, which is representing an Austin instance, we are within the, I say Austin, I should say Stream Inside Azure framework and pipeline. And first, as you've seen on the architecture before, we are in the ingress stage. So what happens in ingress stage, the way I defined it here, is I turned on a few things. First I turned on the spooling, so I persist all these packets. And then I do two transformations here. And that's what I defined in my sample, and that's what I let the cloud instance execute, is two transformations. One is taking the user agent string and translating that into something that's readable, like IE Mobile or Safari. The original string is something very convoluted, and it's not really clear what's the actual user agent. Luckily, there's a web service, so I'm actually calling out the web service, useragentstring.com. With every incoming event, I'm calling out to the web service, let it translate into a humanly consumable browser identification string, and take that and manage my events with that string. And at the same time, I'm also taking the latitude and longitude, taking the GPS position, and make a SQL Azure call as part of my ingress transformation, and transform that into a census block ID. I want to count the, you've seen on the map, you've seen that those are counts. That's the raw data. Those are counts, and they are actually associated with the census block. It's not just the location, because that would create way too many different labels. I want to aggregate that and group by bigger geographic areas, and I'm using census blocks for that. So I first map a geographic location. I just realized that I switched to the map without you seeing it, but you've seen the map with the labels, with the numbers, which are based on the counts within each census block. So I need to get the census block ID from that database based on the raw GPS location, and all of that is done in my ingress stage. And from there, I have enriched my event types. I have created more semantics, more meaning in my events, and I will use these additional properties that I derived in my actual query. And the stream init query that's running here actually is twofold. There are two queries running on that stream. I multicast into two subqueries. Both are grouping. One is grouping by the browser and then counting, and you've seen the bars showing the number of user agents events within a certain time frame. I think it's 10 minutes or 5 minutes. And then I take that result. In this case, I put that into Azure Table Storage using an Azure Table sync in Stream Insight. And then on the other subquery, I group by census block and count there. So I'm counting the number of tags within a census block. And that I take and stream into a service bus endpoint, right? And now I have two event consumers, and the way I'm displaying the data is for the storage, I have created a very simple web page that does some regular calls against Azure Storage. It's an ASP.NET project, very simple, calling to Azure Table Storage, pulling that result and displaying it with a graph, with a bar chart. So that's pulling, but what's more interesting is actually the push model. So that dashboard you've seen, the Bing Maps, it's based on Bing Maps, is a client application running here on my laptop using a service bus endpoint to receive data. So my Stream Inside Azure instance pushes the results into that service bus endpoint. My client receives it right there and is able to display it right away. So it's a true push model, which is a very desirable way to get really event-driven results. And that's the whole pipeline from the beginning to the end, showing to run these expressions within the Stream Inside Azure deployment, and then consume the results. Okay, so we have, let me go through 2 or 3 customer scenarios here that show what other people are doing currently with Stream Inside in Azure. Some of those are actually going into production already, and we are supporting them in a kind of private production environment. First of all is a security software provider. For most of these customers, I can't, since this is all preliminary, can't really talk about the customer itself, but I can still talk about the scenario. So in this case, what this company is doing is processing telemetry events from antivirus and anti-malware clients, and there's a telemetry front end that receives these events, and from there they go as telemetry data items, events into a Stream Inside Azure deployment, also stored in Azure table on the side. And Stream Inside is aggregating the data. What it's doing is it is looking for certain patterns in that incoming stream of detection events from those clients, right? So whenever a signature is detected, there is an event, and if there is a high number of signatures detected, I might have an outbreak of a certain malware or virus. And being able to detect that as fast as possible is, of course, very, very high value. And using an event-driven framework like Stream Inside really helps doing that with very low latency. So those pattern matchings and aggregations are constantly executed against the incoming data, and representing aggregations that then go into a SQL Azure database. In that case, at the same time, there is a web service through an alerting mechanism to a response team, so that I can react on these things, potential outbreaks, as fast as possible. And the response team also has the ability to take the persisted data and use queries to data mine the data and refine the queries, which then potentially get looped back into the real-time deployment to refine and modify the queries based on further knowledge derived from the persisted data. So that's a typical cycle where you have some real-time detections, computations, results being stored, users analyzing the results and figuring out how to refine the computations, and then going back and submitting them into the real-time system. There was a question about the demo in the slide deck, and we can take that offline and see how we can provide that best. It's already been answered. Second customer, this is one I can mention, is Audience Insight, which is the name of the framework that I mentioned in the very beginning, that telemetry processing of video distribution, the keynote chart that you have seen. They have done that not only for the keynote, but for many other video distribution scenarios. MSN, Build Conferences, Channel 9 is using it. And like I've said before, the event source here is a Silverlight player running an Internet Explorer, showing the video feed of the respective events, and at the same time sending back telemetry events about the video delivery, about the user experience, and those go into a Stream Inside deployment in Azure through that REST API, the REST interface, where I have also the possibility to spool that data into Azure storage, the raw incoming data, and do the transformations, like the geo-resolution, debatching, the video client batches telemetry events into single HTTP packets. So I need to debatch them, and I can do that simply through that expression that I define over the incoming raw data. And from there, I go into my queries, like the buffering or the session duration, what you've seen before, the aggregations over time, the number of errors, for instance, and grouping that by location to see is there a certain area, certain geographical area where I have more errors that could point me to a problem with my video distribution network that has a routing problem or something like that. Again, doing all of that in real time. And then persisting that in the database so that I can have a dashboard feeding off that database using, in this case, the OData interface to display and make that humanly consumable. So again, typical example of how to integrate Windows Azure Stream Insight into that end-to-end telemetry analytics use case. That's another customer that is currently using the service in its CTP phase. In this case, that customer in that scenario wants to process telemetry events from cell phone users to reason about their behavior and then feed back information to the user. They have their own service front end from where data is then collected and sent into the Stream Insight Azure deployment. And what they do from there is two things. They also do the raw data spooling, the storage, but also they have, in this case, I think more than 60,000 events per second. And using a database right there would just not be very feasible to persist all that noise, basically. Instead, they use Stream Insight to aggregate in real time in the cloud every 60 seconds for the last 1 hour and persist that in a SQL database from where I can now run reports against the pre-aggregated data and aggregate it even further, roll the data up even further. But what they're also doing, what is very interesting, is use the raw incoming data. They don't want to lose that information, just not put it into a database right away, but use MapReduce frameworks to data mine that information and then derive further knowledge from that and put that into SQL as well. So there is, again, this whole cycle of finding out information, persist that, finding out more based on the historical data, have a kind of a data scientist workflow against the historic data, finding new queries, finding new models, and then putting that back into the real-time deployment. And that's a typical pattern that we see very often happening around event processing and event-driven deployments. All right. I'm almost done here. Let me talk about the roadmap. We mentioned here the June CTP. In the meantime, I have to admit I'm reusing a slide deck that's a few weeks old. In August, we have updated our CTP. We call it the August CTP, surprisingly, which added a few features like HTTPS on data ingress, for instance, which added the dependency on Azure SDK 1.7. That was a big ask from customers who wanted to be consistent with their other Azure development efforts and be able to use SDK 1.7. So we had a few updates there in August. We are looking at going into a public preview, even being available on the Azure portal and having some further features implemented by the end of the year. And I say that very tentatively, as you know, as we usually have to do it, because we can't commit to anything at this point, but that's our effort. And then later next year, hopefully not too late next year, we want to be able to make the service generally available with a finalized business model, with a pricing model, and have a production-ready service with an SLA, providing Stream Insights in Azure. And related to that business model, a few more words about scale. I briefly mentioned that this is in effect a single tenancy service. So what is really one of the central design tenets and goals is to make performance predictable and dedicate compute resources to use cases. So if you have tens of thousands of connected clients, and you know you will need multiple cores and multiple VMs to process the data, you can be sure that nothing else is running on these machines except your code. So this helps us with providing a level of security and privacy and encapsulation, as well as predictable performance. So you get dedicated capacity and consistent, repeatable performance. In the current version of the CTP, We don't scale out the analytics node that runs the Stream Insight engine. We just scale it up from 1 to 8 cores, but we do scale out across multiple VMs the ingress stage where the stateless event per event transformations are running. So it is already providing a transparent scale out way of processing streaming data. And the model of dedicating machines and cores to customers really help make the service predictable and dedicate capacity. All right, I think it's probably my last slide. Resources. First of all, if you're interested in participating in CTP, it's private, but it's not restricted in any way. So just email me that alias at Microsoft.com or my colleague Tiho. And there are a few Stream Insight resources. If we can make this deck available, you can just click on the links, search for Stream Insight. There is not that much information about Azure Stream Insights because it's not really a public service yet. We have blogs about it, but most of the public information is about the core Stream Insight. And with the cloud service, we are still in the CTP phase without that much public available outreach yet. That's all I have. Thank you very much. We are pretty much on time. We have, I think, 5 minutes left for questions. Let me know if I should.
Yeah, and if anybody has questions, just use the Q&A feature through Live Meeting to post your questions, and we can tackle them one by one. So we'll give folks about 30 seconds to get their questions in there, and if we don't see anything, we'll move on.